Okay, types of aqueous solutions. So we got salt water and sugar water. These are both familiar. Salt water is a mixture of salt, sodium chloride, and water. Sugar water is a homogeneous mixture, a solution of sugar and water. And you put a teaspoon of either into a glass of water and you stir it, and it looks like it's disappearing, right? How does that happen? What's going on? Well, a number of things are going on. So let's look at this picture. So here in the purple we have our solute molecules. Could be the sugar, could be the salt. Why is sugar a solid at room temperature? Why is sugar not a gas? Why is anything a solid? Because there are forces of attraction that hold the particles together. So there are attractive forces between the solute particles. Why is the water a liquid? Because it also has forces of attraction between the molecules. So there are forces of attraction between the solvent molecules. In order for these two substances to mix together, there also have to be significant interactions between the solvent and the solute. So all of my ancestors came from Sweden. All of my husband's ancestors came from Japan. So I'm going to pick on the Japanese and the Swedes, and no one can accuse me of anything, okay? So let's pretend that this is a bunch of Swedish people who only speak Swedish. It's not true, most of them also speak English, but we'll pretend. So these people only speak Swedish, and these green people over here only speak Japanese. So these purple people have a lot in common with each other. They can communicate, and part of being attracted or getting along with other people is being able to communicate with them. And the green people are good with each other because they're speaking Japanese to each other. But if the Swedes and the Japanese cannot communicate with each other, are they likely to mingle? Imagine a big group, a big conference room, and you've got like 50 Swedish people and 50 Japanese people. Are they going to all just intermingle if they don't speak the same language? No, they're going to form little clusters, right? You're going to hang out with the people you can talk to. It just makes sense. That happens with molecules too. If the molecules are attracted to each other and not to the other kind of molecule, they're not going to mix. They just won't. If the attractions between the solute and the solvent are strong enough, then the solute will dissolve. In order for these purple molecules to separate from each other, that attraction, that comfort they feel from their other solute molecules needs to be replaced by an attraction to these other solvent molecules. Let's look at a water molecule. So this water molecule looks a little different than the ones we've looked at before. Here's the oxygen atom, and here are two hydrogen atoms. There's a covalent bond between the oxygen and the hydrogen involving a shared pair of electrons. The electrons are shared, but just because something is shared doesn't mean it's shared equally, right? If you've ever shared a bed with someone, you probably experienced unequal sharing of the blanket, right? Someone is always taking it from the other person. So here oxygen's hogging the electrons. So oxygen has more blanket than hydrogen does. So oxygen has more negative charge, hydrogen has less. So it's slightly positive. It's lopsided, okay? This is not an ion, but one end of it is a little bit negative and one end of it is a little bit positive. So let's talk about sodium chloride. It has sodium ions and chloride ions, right? The positive sodium ions are very attracted to the negative chloride ions. They're just really good with each other. They don't want to separate. But here comes a water molecule. The negative end of the water molecule is attracted to the positive ion. Now that's not enough of an attraction to completely replace this attraction, but it's a start. And the chloride is attracted and attracting the positive end of other water molecules. Water is sort of a two-faced molecule. It can appear to you positive, or it can turn around and show you its negative side. You know, it's like, well, what do you want to see? I'll show you that phase. So here we have a sodium chloride crystal dissolving in water. The water molecules are attracted to the charges on these ions. And here we have a positive sodium ion that's surrounded by water molecules showing it their negative side. And so they sort of come around and they lure it away from the larger crystal. Oh, come out and play with us. We'll make you feel good. You know, you can come out and be with us, and we're attracted to each other. And then over here, the water's turning its other side to the chloride and doing the same thing. And so these ions now are able to move out into the water. And they're not stuck here next to each other anymore. Does that make any sense? The result is, in a saltwater solution, we have sodium ions and chloride ions that are free to move through the solution. That allows that solution to conduct electricity. Electricity is the flow of electrons. In order to conduct electricity, you have to have charged particles that can move those electrons back and forth. So we call a saltwater solution an electrolyte, or an electrolyte solution. Electrolytes are substances that dissolve in water and form solutions that conduct electricity. These are definitely going to include all soluble ionic compounds. If you have pure water in a beaker and you hook up a light bulb and a battery and 2 electrodes, the light bulb will not go on because there's nothing to connect these 2 electrodes. In order for the light bulb to light, there has to be a closed circuit for the electricity to run in. And as the electricity runs through there, it makes the filament glow. If we put salt in the water, the salt dissolves, and the sodium ions and the chloride ions are free to move, and they can conduct the electricity, and the light bulb will go on. Throw salt in the water, and it's like you turned on a switch. If you put sugar in the water, nothing's going to happen. Sugar dissolves also, but it doesn't form ions, and so there's nothing to carry the charge. So sugar is a non-electrolyte. Non-electrolytes do not conduct electricity because they don't form ions. And this would include most molecular compounds. Any questions? So here we show how sugar can dissolve in water. Sugar is a molecular compound. It's got a lot of oxygens and hydrogens. And in this compound, oxygen and hydrogen are also not sharing the blankets evenly. So all of the hydrogens are a little bit positive, all of the oxygens are a little bit negative. And so the water molecules are also attracted to various parts of the sugar molecule and kind of come along and escort it away from the rest of the crystal. The water is replacing the attractive forces that were holding the sugar molecules together as a solid. So the sugar floats around, we get a thorough mixing, a homogeneous mixture, but there aren't any ions, and so this will not conduct electricity. So here's a question you may or may not be thinking about. If pure water does not conduct electricity, why is it dangerous to be using electrical equipment when you're standing in a puddle of water? Why is it dangerous to be around water, big bodies of water, when there's an electrical storm?
Is the water that you're around isn't pure water?
Bingo. The water you're standing in on the deck or the patio, sawing something, is that pure water? No, it's definitely not pure water. Even the water that comes out of the tap is not pure water. It has some dissolved minerals in it. So tap water will conduct electricity. Not real strongly, but it will. And then if you're dealing with lightning, that is so much electricity that, all bets are off. We've learned a bit about acids. So here's a little more about acids. We learned that acids are molecular compounds, things like HCl, 2 nonmetals, right? But when an acid is dissolved in water, it forms ions. We say it ionizes, it forms ions. So the molecules are really pulled apart by their attraction for the water. So the hydrogen ions and the chloride ions get pulled apart from each other. In a strong acid, the acid ionizes completely. There are no intact molecules of HCl left in an aqueous solution. They all separate into ions. A weak acid, though, will mostly remain as molecules and only form a few ions. So it'll just ionize a little bit. This arrow only has one head. It's pointing to the right only. This reaction goes to the right. The hydrogen and the chloride do not come back together and form molecules in the water. Here, these are two weak acids, and the arrows here have two heads. They're pointing in both directions at the same time. So hydrogen fluoride or hydrofluoric acid ionizes to form hydrogen ions and fluoride ions, but it also has this other reaction going where the hydrogen ions and the fluoride ions can come back together and make the molecules. So here's an illustration of a weak acid, acetic acid, and we see that some of the molecules have ionized, but most of them have not. And that's characteristic of a weak acid. Weak acid does not mean it is not caustic, it's not dangerous, it won't burn your skin or destroy something that you're putting it on. It just means that it doesn't ionize completely. So strong electrolytes, the substance dissolves completely to form ions. So soluble ionic compounds like sodium chloride do that. Strong acids also do that. Those substances in solution will conduct electricity well. The light bulb glows strongly. The bright is light. The light is strong. Is the weak over yet? In a weak electrolyte, you have mostly molecules, but a few ions. And so this would be the weak acids. More pictures. So here we have a sugar solution. Put sugar in the beaker, the light bulb doesn't go on at all. Yeah?
So since Gatorade has electrolytes in it, would be considered a weak acid?
That's an excellent question. So Gatorade has electrolytes in it. Would it be considered a weak acid? It would not be considered a weak acid, but it would be considered an electrolyte. So it is a strong electrolyte, and the use of the word there is the same as how we use it in chemistry. It means a soluble compound that forms ions. And your body needs ions. If you've ever, who hasn't had sweat running down their face this summer, right? And it gets in your mouth and it tastes salty, right? Because there's salt in it. There's sodium ions and chloride ions and other ions as well. And if you go out and you work out a lot, especially in a dark shirt, and then you let that shirt dry without washing it, that's kind of gross, but you know, it happens. You've got these white crystally stuff on there. That's salt that came out of your body, right? So when you sweat a lot, you lose a lot of ionic compounds. It's not just sodium chloride. And so then you need to replace that. Now the thing is about things like Gatorade, they also have a lot of sugar in them. And the sugar it makes it taste better, but it doesn't really do you much good.
Water that has it as well.
Pardon me?
There's water, they sell water that has
Yeah, they're also selling some other things, water that has dissolved minerals and things, and those don't necessarily taste as good because they don't have all the sugar, but they're probably a lot better for you. The thing is, unless you're sweating a lot, just plain old water is probably going to be good enough because you also get a lot of electrolytes from the foods that you eat. But for, like my boys play football and they're out there and it's 106 and they're in full pads going at it, they're sweating a lot. They probably need some added electrolytes. Excellent question. Okay, here we've got sodium chloride. Sodium chloride separates into ions completely. It's a strong electrolyte. The light bulb glows very brightly. It's a strong light. This is a non-light. There's no light. Here's a weak electrolyte. So it's glowing, but the light is weak. Okay, if that helps you remember. So we just talked about acids ionizing. They are molecular compounds, but they form ions when they dissolve. What about, I don't know how to do that. What about an ionic compound? An ionic compound doesn't technically ionize because it already has ions, but the ions dissociate. Association means coming together. Dissociation means going apart. So the ions separate from each other. So here's an example, sodium sulfide. Sodium ions and sulfide ions, they are together here in the formula. When we dissolve that in water, they separate into sodium ions and sulfide ions. So one thing that's sometimes confusing to students is, well, there was a subscript 2 there. Why isn't this Na2? Well, let's think back to nomenclature and how did we learn to identify the different ions, right? And how did we learn to write the formulas? We looked at their charges, right? And so sodium is just Na, and it's got a positive 1 charge because it's in group 1. And we learned that sulfur forms a 2- ion. And so when we write the formula, we look at the relative charges, and that's how we end up with Na2S. The 2 means that we have 2 sodium ions with 1 sulfide ion. So when we write the equation for dissociation, we use the individual formulas of the ions, and we use coefficients to tell how many there are. Here's sodium sulfate. Similar, but different. This is sodium sulfide, this is sodium sulfate. Another thing that happens to students is they look at that and they're like wanting to split it into 3 things, because there's 3 elements, right? But in Chem 1A, there's always 2 ions. 1 kind of cation, 1 kind of anion. So here, the metal, sodium, is going to be the cation, and so that has the formula Na+. This 2 is because in this formula, pointer, in this formula, there were 2 of them. And then if I cover up the sodium, what's left, SO4, that is the other ion. Don't try to take it apart. So I've got sulfate ions. Any questions? So ionic compounds, when they dissolve in water, we've got separated ions. The thing is, not all ionic compounds dissolve in water. We say that a substance is soluble if it dissolves and insoluble if it does not dissolve in water. And those are qualitative terms. The truth is that even an insoluble compound, come on, pointer, even an insoluble compound dissolves to some extent, okay? Random analogy came into my head. Someone can say, well, I'm not a liar. I don't lie. Okay. Does that mean you never, ever, ever lied? You've never, ever told a lie in your whole life? No, probably everybody's lied at least once, right? Even an insoluble compound dissolves a teeny tiny bit. Now, if you put a whole chunk of it in a big vat of water, maybe you get 5 ions forming, but that's still something, right? Now, maybe it's not significant, but even insoluble compounds dissolve a teeny tiny bit. Let's look at 2 different silver salts. So here we've got silver nitrate, and here we've got silver chloride, AgCl. Silver nitrate dissolves in water very nicely, forming silver ions and nitrate ions. If we put silver chloride in water, though, it seems to just sit there and do absolutely nothing. You can stir it, you can wait, you can swear at it, it's just not going to dissolve. Why does one dissolve, the other not? Oops, having issues. Well, the short answer is it's complicated. There are multiple factors that cause one compound to dissolve and another one to not dissolve. They're not easy to predict, and so we're not going to go into them. We're going to use what's called an empirical method, where people have tried dissolving all these different things in water, and they made a list, and we looked for common patterns in the list, and so we've got some rules. The rules are not infallible, but they work most of the time. So this is a table 4.1 from your textbook, the solubility rules for ionic compounds in water. I am not going to give you this table on an exam. I'm not going to let you use the green card on an exam. I'm also going to tell you the information on the green card is not exactly the same as the one on this table. It's got some more information that this one doesn't. This is the stuff I want you to remember, to memorize. Now that table looks a little scary, doesn't it? I'm going to actually erase most of it, and it's not going to be that bad. So this is how you do the table. The top half are compounds with these ions are generally soluble, and then it lists some exceptions. In the bottom half, these sorts of compounds are insoluble with some exceptions. So if you just go through from top to bottom, then we can actually erase a whole bunch of this stuff. So you look at your compound. Does it have lithium, sodium, potassium, or ammonium ion in it? If the answer is yes, it's soluble. You're done. Doesn't matter what the other ion is. Notice that lithium, sodium, and potassium are group 1A metals. And then there's ammonium, and he's just weird. The next one is nitrate and acetate. If it's got nitrate or acetate in it, it's soluble, no exceptions. Then we get to chloride, bromide, and iodide. These are, I think of them as three sisters. Their last name is halogen. They are generally soluble, except, now we do have an exception. We've got silver, mercury 1, and lead 2. Now, I am not going to trick you with mercury 2 versus mercury 1, or lead 2 versus lead 4. I'm not going to play games like that. So you don't necessarily have to remember those charges as silver, mercury, and lead. So we really don't need all those words in there. Silver, mercury, or lead. Okay, sulfate. Sulfate things are mostly soluble, except here we have strontium, barium, lead, calcium, and silver. So the lead and the silver are the same as up there, and then strontium, barium, and calcium are group 2A metals. So those are the exceptions. So if you get through all of those and you don't have any of these guys, then you can get into hydroxide and sulfide. So this one, when these ions pair with lithium, sodium, potassium, or ammonium, the resulting compounds are soluble. Well, we don't really need that, because if we start at the top and work our way down, if we have one of those, we're not going to get down here, right? So we don't need to think about that as an exception. So that one just goes away. Okay, if sulfide pairs with calcium, strontium, or barium, the resulting compound is soluble. Calcium, strontium, and barium, those are three of the ones that were an exception with sulfate. Oops. Went too far. And this next one, when hydroxide pairs with those same three things, the resulting compound is slightly soluble. Okay, well that's enough of an exception. I am not going to try to trick you on soluble versus slightly soluble. So we can erase that as well. And just say strontium, barium, and calcium are exceptions to these two guys being insoluble. Then we have carbonate and phosphate. And again, we have lithium, sodium, potassium, or ammonium. Well, if we start at the top, we're never going to get down there, and so we don't need that either. Okay, does that look a little more manageable? So you go through these in order. Alkali metals, ammonium, soluble. Nitrate or acetate, soluble. The halides, chloride, bromide, iodide, they're soluble except with silver, mercury, and lead. And then sulfate, soluble except for strontium, barium, calcium, lead, or silver. In the bottom, we've got hydroxide and sulfide being insoluble except with calcium, strontium, or barium. And at the bottom, carbonate and phosphate, insoluble. So what you should do as you go through your homework and various things and have to ask yourself, is this soluble or not? Try to do it from the table that you make in your head, and then check yourself. If you do it that way, you can learn this without too much effort. If you always look at the green card, then you're not going to remember. Okay, predict whether each compound is soluble or insoluble. So, nickel sulfide. So we have two ions here. We have nickel and we have sulfide. If you go through that list, neither of these is in the top half. So we get to the bottom of mostly insoluble and we see sulfide. The exceptions for sulfide were calcium, barium, and strontium. This is not one of the exceptions. So nickel sulfide is insoluble. Magnesium phosphate. If you start at the top and go through the list, magnesium's not in the top and phosphate's not in the top. When you get down to the bottom, phosphate's way at the bottom. If you've gotten down there, there's no exceptions. Phosphate with magnesium is insoluble. How about lithium carbonate? Soluble. Because in that first row, lithium, sodium, potassium, ammonium, always soluble. So this one's soluble, and we don't even have to go any further. Ammonium chloride, soluble. Again, ammonium's in the first row, so this one's soluble. So that's how you predict solubility. You start at the top of the table, and you go until you find one of the ions in your compound. Then you have to say, well, am I in the soluble part of the table? Am I in the insoluble part? Is this an exception or not?